So like I'm Bangali. Okay, so I
Oh,
was like I did some information about like some other language from the same region. So like are you like like native Hindi like Hindi speaker?
I'm actually native Marathi, but yeah,
Okay.
Hindi also.
Okay, like you're into this so there's a thing I'm working like particularly right now on like
Mhm.
on Bangla, like there's a concept called Sandhi. So this is something like that two separate word, two different word joins merge as a same word, but there's a like I think the difference from other language is that the like whenever the two word merges, end of the
Mhm.
first word and the beginning of the second word they changes little bit. So for instance, cholot chitro, so that changes to cholo chitro. So is there something similar to your language, Marathi?
Let me think.
Sorry, repeat.
Yeah, I'm just thinking whether
Okay,
it's
okay, okay.
whether there's a pattern like that. I don't think so. Every I think any combination of words in my language is spoken of on its own, very enunciated very clearly on its own. So there's nothing of this pattern that follows in. I think even in Hindi there's nothing like this.
Oh, okay, okay. I thought like there would be some similarity, but
No, no. I think there might be a few foreign languages. I learned French a while ago in my school, and I think there's something like that there, where two
right.
words that are like immediately one after another. Some words like that do form a different pronunciation or meaning altogether.
Like I like there are few languages like Finnish, German, like that does that, but
Yeah.
that later like in written word, like or the pronunciation
Mhm.
doesn't change. It just stays the
Mhm.
same. But in Bangla, like it changes. So I think it's
Yeah.
like
Yeah.
Okay. So curly coder, we
I'm
can,
sorry.
yeah, we can get started with chapter 5.
Okay. Just let me know, guys. I'm just sharing my entire screen.
Mm-hmm.
Uh, just let me know if it's visible.
Yep, yeah, we can see the screen.
Yeah, you too,
can you
Shishir.
wait one moment because I'm gonna like screen share. Like do you mind
Screen record,
doing
actually.
recording? Yeah.
Okay.
Yeah, no
And
worries.
I'm also recording. Okay.
Uh,
Um,
uh, okay. One more thing, actually. So I think you have an EPUB file, but do you have the link attached to the PDF, like the EPUB file?
oh, the database internals file.
Yeah.
Um, Wait, I need to see. I think I share. Yeah, I shared the link in the Discord, but PDF. I think I shared the PDF link only.
Yeah, you did. I think it's
No,
lost in the
It's
chat somewhere.
it's
my
PDF link.
concern is like
It's
some
in
of the
no, it's
references.
in the database channel.
Oh, okay, okay. No, no, no. My concern is like something else. Like my concern is that some of the what is the word for it? Like some of the link that leads to the database internal book. Okay. So some of them like link to the database internal book. So in the database internal book, what is the word for it? Sorry, database internal website, but none of those link works.
I know. Yeah.
So yeah, that's possibility.
Okay.
I don't know. I will see if there is any updated PDF version or not.
Yeah. No, no, no.
The
Like
PDF
when
link that I shared, it also doesn't have like the table of contents as well. I separately shared the table of contents. So I'll have a look if there is an updated PDF version.
but I think the PDF is fine. The website is like link doesn't work within the website.
Okay.
Hey, you use the Obsidian tool?
Yeah.
Yeah, like there was like really nice looking like graph in there.
Yeah, I've added a few plugins there.
Okay.
Yeah, guys, let me know if I can start.
Yeah, sure. Let's start.
Okay. Is it fine with you guys that I go back and forth between the highlights and the notes that we have, so that I'll
Huh?
It's
also
fine.
be using the, yeah?
No, it's fine. It's fine.
Okay. Okay. So I think, yeah, let's go over, I'll start with the high level view of what this chapter covers, and then we'll dive into all the concepts in detail. I have skipped a few things that I could not find any important more explanations on in the textbook itself, or anything in the open source implementations, such as I have very little gone. I have just skimmed through page replacement and some of the lock based concurrency control ones. But I think apart from that, the core of the chapter is mostly covered. But yeah, we'll go through them one by one. Yeah, so starting off, the chapter is basically just as the title suggests, it's about transaction management at its core, but it consists of three components, right? We'll come to that. But let's, from the first principles point of view, why the textbook suggests why transaction management is needed in any production grade database system is because you want to enforce some variants, some invariants that the databases have to maintain, right? That's the why of any transaction management system. And on a very high level, it's managed. There's a component called as a transaction manager. It's mostly just a logical concept in any database system, but it consists of three components, which is managing buffers, recovery. As we all know, we want to recover from all the crashes, and then the concurrency control, which changes depending on the storage engine, right policies, and the type of and the use case that a database is built upon. But we'll come to that, right? Yeah. So let's come to the basics of what a transaction manager is, what a transaction is in the first place, right? As the textbook suggests, it is an indivisible logical unit. It's basically any transaction. Let me just come to this. I think, yeah, what basically it says the same thing. I've taken the notes from the textbook itself, but what it suggests is it's a sequence of operations that are coupled together, represented as a single step. That is why, even though it's a sequence of steps, the database sees it as atomic. Either the whole transaction occurs or not, which is also what we call as atomicity. But yeah, a transaction is supposed to comply with ACID rules of a database. So I think every one of us might already be aware of the ACID, but I'll just quickly go through them just for the sake of setting some context. Sorry. So atomicity is just either the transaction completes as a whole or it doesn't at all. We abort it and roll back every change that the partially completed transaction did. So either we persist the full state of a successful transaction or we abort the failed one. Consistency is it's a broader term because it refers to application specific guarantees. It can be something like, I'm so sorry, I don't know why this is happening. Something like a foreign key constraint or any invariance that an application or a database might put forth. So coming to what these invariants are, these are not covered in the textbook, but I wanted to understand what the invariants are. But it's pretty much what we already might be aware of. It's the referential integrity, I think something that foreign keys cover. Business rules that any SaaS or any application that's actually using a database will dictate. That's very application specific, and the rest of it are just more of these two constraints. So why these are called invariants is because regardless of any transaction that or any amount of transactions that happen that have anything to do with updating a database state, there are some rules or properties of a database, like the 5 that are described here, that never change their values, right? That's or they never change how they look like from a database perspective. That's why they're called as invariants.
Okay,
This
in the book, is it is it covered that how these invariants are checked? Is there anything mentioned regarding that? Like how we
how
efficiently?
these invariants are checked, yeah, from a perspective, not from the 5 points that I've mentioned here. That's something I got from Google, but as a larger concept, yes. How the textbook talks about how invariants are enforced, and that's implied through preserving asset, is what the textbook talks about. So I think in the recovery and the concurrency control section, it talks about how they are done on a transaction level.
Okay.
Yeah. I think that is the what and the why. Yeah, let's actually. Yeah. So there's a few terminologies or basic concepts that we might need to know about. So we have now come into the buffer management section of the transaction manager. So before going deep into buffer manager, we'll talk a little bit about all 3 of these. So the 3 components for managing a transaction is buffer management. That's basically since all the operations on eventually are on disk, we want to optimize a lot of the reads and the writes to that. So the primary way of any DBMS of handling all the operations is through first in an in-memory structure and then via the disk, right? So that's a lot of what a database interacts with the in-memory structure is handled through the buffer manager. So yeah, so a buffer, yeah. So before that, there's like 3 concepts we need to know. The first one is page cache. I think if any of you know about virtual memory, it's the similar concept. It's inspired by how operating systems handle virtual memory. Databases also have a concept called as a page cache. This is different from virtual memory, but it's sort of similar. But basically, how any DBMS operates is that the persistent storage that is on disk, between the operations that happen on the database and the disk, there is one more layer, which is an in-memory structure. Broadly, it's referred to as the page cache. Pages are anything that the architecture supports. Sometimes it's 4 KB up to, I don't know the upper limit. I don't have knowledge of that, but I think somewhere in so basically the whole communication happens in pages. They load pages from disk in memory, and they deload pages from memory to disk. That's how broadly it goes.
Just 5 minutes. I'm actually building one myself. I'll just add the links to the Substack articles I'm writing for a page cache. I'll be using LRU replacement algorithm or a clock algorithm. I'll just put in if anybody wants to check it out, it's single.
Yeah. I had some links that I plan to share once the call was over. I think we can just put it as a reply to this thread. So it's just one link.
Okay, by the way, so I know about this paging and virtual memory and how it works in case of operating systems, but how do we relate that with this like page cache in databases? Is it like for the physical disk, all the blocks are mapped to memory pages somewhere, and we maintain some kind of table where these mappings are inserted and deleted?
Yeah, so similar to the operating system, database also has this page cache, but unlike an OS which maintains physical frames, if I'm not wrong, in the physical memory. I think it's in the physical memory. Databases have just have a preset of what every page does. So, for example, I remember from how SQLite does it is that it has I don't remember the exact number, but if it has something somewhere between 1 to 100 pages, they have the metadata stored in page number 0 about what each page is going to do. So what they do is they say that page number 1 to 5 will just store the metadata such as the schema tables, the number of tables and what the schema of each table is. And then the 6 to whatever the other tables are, they will store the data on that. So the pointers to this, all these disks is maintained in memory. So this is inspired by this, but it's similar that they have an in-memory, to answer your question, basically they have a in-memory storage where they maintain all the mapped pages to the physical disks. But we'll come to that in the write-ahead log, how they model this.
Okay.
Sorry, could you repeat that? I didn't get it.
Which part?
Just this one in general. You're talking about SQLite. So I built one, but it was very simple. So what I did was on top of this, I was using a B tree to structure all the data. So each node in the B tree was corresponding to each 4 KB page in the data in the file. So what essentially what I'm doing is I'm caching nodes of the B tree. So that is for key value pairs because I'm like storing key value pair. I didn't understand what it is in reference to SQLite. You just explain that again. You were talking about metadata.
Oh, all right. So if I don't know if I have it. Oh, yeah. Okay. So what I was referring to is they have somewhere they mention that pages are numbered. There are what I was mentioning was that they have a fixed number of pages for I think like the first 2 or 3 pages or something like that, and they have set number of offsets about what each offset in that page describes. For example, I think this is one, the database header. This is I think always in page number 1, which is sort of considered hard coded. Is that page number 1 will have the database header.
Okay, so these are like basically these are fixed pages that we already know what each page that those specific pages what do they have. Like for example, a free list.
What is the payload fraction? Sorry?
No, I was saying so. What you meant by that is when the database starts up, it reads these pages whose meanings are fixed. Like let's say it's hard coded that the pages 0, 1, 2 are going to have this kind of data about the database. So that is just read into memory and kept there for the entirety of the process. Like it's not it's maintained there.
Yes. Yeah.
That's what you meant. Okay.
Yeah.
Okay. Cool.
Okay. Yeah, so that was about page cache. They have talked about page cache in a very broader term, if I'm not wrong. And further up ahead in the chapter, they actually talk about page cache from a write-ahead log sort of perspective, because log, which will come to obviously, but I think what they refer to as the in-memory structure is there is a in-memory structure in front of the write-ahead log, as well as an in-memory structure in front of parallel to the write-ahead log, but in front of the main persistent storage. So yeah, I think we'll come to that in a moment. Yes, and for a few facts, I think all changes to a database state, which is any changes that are supposed to go into disk, are first applied to cache pages. It's also important to know when the textbook says in this chapter that a transaction is committing. What we actually mean is committing to memory. Anything that a transaction does is first in memory, and then it's flushed to disk. I think I've seen the textbook refer to it as an fsync call, but I'm not sure if there's any other ways to do it. log manager also very high level term. It just refers to further up ahead in the book to the right ahead now. So yeah, coming back.
Sorry, what did you say was the fsync call? What was it referring to?
Fsync is a Linux kernel call that basically
meant to, so that the OS doesn't buffer on its own. So if for optimization sake, sometimes the OS also buffers your writes. We don't want that because it's possible that the OS buffers it and actually doesn't write it to disk. And then everything crashes. So your writes are actually lost because the OS was buffering it. It didn't actually write it, even though the database thinks it wrote. So fsync is just for that, so that it doesn't buffer.
fsync does transfer data to the actual disk, right?
Yeah. So it just tells the OS not to buffer any writes. So as soon as it gets something, the OS should just directly write it to the disk without collecting up writes for the sake of optimization.
I remember correctly. I think it tells the buffer to put on the disk, whatever is inside the buffer to put in the disk. I shared something on the data server. Wait, let me reply. It's on the database chat. This is about there's file system developer and the database developer. They're fighting over fsync implementation. So this is really cool forum kind of thing you can look at.
Okay.
Yeah, this.
Tells the operating system to flush the whatever is in the buffer to the disk. That's what you're saying.
Okay, so I have a question then. So that tells the OS to not buffer anything, which means does it buffer by default, the operating system?
Yes, I think it does. Sake of optimization, it buffers.
Another example can be TCP no delay. There's a by default, the value is 0. So what happens is that whenever from the application, you're sending some sort of data, whatever it is, from your application side, you have already sent the data. But if TCP no delay is set to a certain value 0, then it will not send the data. It will wait for certain value to the packets, total amount of data is supposed to send to a receiver, certain value to be certain threshold to reach. After that, it's going to send the data. So it does that for all kind of tasks.
Sort of it batch sends all the packets. That's why we want to have a delay.
So I think that on the sender side it doesn't continuously send the data because on the receiver side it's not supposed to buffer it. Is that what you mean? I think that was for the placement.
I sort of did not get the no delay example in the context of this.
No, if you look at yeah.
Please.
You ask me, if you have any question, you can ask me.
Okay.
Yeah. So
Today, where should I?
Yeah, you can have the link.
Just don't want to rely on Quora.
Yes. Okay. You can think same as flashing, but it's storing the packets or storing the whatever the one receiver is supposed to have. So, but if certain if the buffer size increase to some certain value, then it's gonna send it. Before that, it's just gonna hold that to buffer.
Oh, okay. Got it. Okay, so in the context of fsync, that's what you meant, is that buffering until you reach some arbitrary that wants to optimize the right.
Yeah. Okay. Was I have read about it 2 years ago, so I think.
Okay. I think I
not say.
See, I mean, if every time you do an insert, every time you try to insert a key value pair, if it does a syscall and tries to write that key value pair into memory, doing syscalls is pretty expensive. So what we do is in memory we keep storing, we keep delaying these things, and we store the updates in memory. Once the buffer is full, what we do, we call fsync, which is a system call, and that batch flushes all the key value pair updates to the disk. So we have like
Yeah.
less
Yeah,
expense on
yeah.
that. So that
Okay, but what happens if it crashes before the buffer can be written? Isn't it
It's gonna
lost?
be lost.
we have
That is,
walls for that. So we have two things. One is of course that like in the disk those key value pairs, and we also have wall where we keep a log of like what activities we are doing for the database. So
I'm
when
familiar with
we
that concept. So for wall, what it will be written without buffering then.
yeah, to the wall
uh,
it's written directly, like any operation we do.
okay, actually, I think like it's not always written like well, if I like remember correctly.
Then
Sorry?
then yeah, if it
Because
crashes, how do we keep track of, like we lose some data then.
yeah, because
Yeah,
thing is,
so
yeah,
yeah, one thing about durability is that 100% durability is never considered to be promised, because any hardware at any level or software at any level will fail. So I think it also talks about that, yeah, asset compliance, the compliance to durability is never 100%, because there's a lot of reasons when you'll just lose your data. It might be bit rot or it might be anything else. I think that's one thing. But I'm not sure how what syscall they use for, or what syscall is considered idiomatic for writing to a disk resident wall. I'm not sure about that.
Okay.
no, because like what I was thinking that if you're writing in WAL, like you on the disk, it's the same as like if you're writing the actual like data record, right? Like both of them are same expensive, so WAL shouldn't have been used. Like you could just write the database entry.
Yeah, yeah, that does make sense.
So just to clarify, Epstein forces any cached writes to go to be written to the like disk. So it forces the OS to write.
Yeah,
That's what I understood.
yeah. That's how I understood from this. But one thing, when you mentioned that it tells the OS to not buffer, that's where I was slightly confused.
No, I think I was wrong. It forces it does buffer, but then Epstein forces any write that is buffered to go like it should be written. I think
Yes.
Yeah,
it's
yeah,
like
exactly.
Yeah.
Yeah.
okay,
Okay.
yeah.
Okay. No worries. Oops, sorry, where was I?
Did
Yeah.
any of you like looked at like Dice DB? Like, I think it just came out like 1 week ago or something.
I saw a video of it,
Yeah,
some
I
1.0 version, but I've not gone through it.
I was taking a look at the source
What
code
about it?
last October.
No, like I wanted to look into it, but I'm so
Maybe
busy.
maybe.
But I think it would be good.
And
Yes.
if you want a partner for that, I'm down. If we can go through
I'm
it together.
busy for like
I'm pretty good
after
at
that.
Go.
I might like go through the code. Yeah, it really looks promising. Like, yeah.
One
Oh,
thing
it's written Go. Okay,
The
okay.
problem,
one thing I'm interested
I'm
is
staying influenced with that. So
one thing I'm interested about this is how they implemented this shared nothing architecture here. That's the interesting part, I think. I think we have Dragonfly as well, which is like an alternative Redis implementation where they
Yeah, that is
also.
good too. Yeah. Then, did you look at Red Panda? Like, that is cool, really cool too.
I mean, I used it, but I didn't take a look at the source code.
Okay.
Yeah.
my question being gone through this.
Like the one I replied to on the database, on the database like channel, like I replied to like one of the forum post. Yeah, this one. Do you mind opening it? Yeah.
This one?
Yeah, this one. Yeah.
Is this the same one where the author of Limbo, I guess, is talking about this? Sorry, author of Tiger Beetle and someone else.
Yeah, Tiger Beetle. Yeah. I was
Yeah.
like, okay, why?
Yeah, I know this was getting extremely furious.
You played the game Limbo?
Sorry?
Any of you played the game Limbo? Like the game name was.
Yeah, I have.
Yeah, that was a really great game. Yeah.
Wait, why is this is not opening?
I have no idea. Let me see if I can open it.
No, it's opening for me.
Do you guys have any experience going through this like really large code bases that the one ISTB has? I'm interested, but I don't really know how to like where to start.
I think not a database one. I did go through this one. I was sort of on a reverse engineering stint for this one. I ported this implementation in Zig. I don't know. It's not a large enough per se, but it's sort of, yeah, it is a bigger code base relatively.
Yeah, so like the number of files are crazy, right? How do you how do you know where to start?
I think for particularly for this one, they had an academic paper, and then they had also had a internal stock. So I knew I had to start from the one file, which was I think this one, and the other one. So I think I started with just one or two files and worked my way up through first reading the tests and then sort of just debug logging any flow that I wanted to reverse engineer.
Okay. Okay.
But it will feel uncomfortable in the beginning, like.
Oh yeah, it's yeah. I think it took me like 6 to 7 odd months, and no, I think it took me about 9 months. But that was only because this is a Rust code base. Rust is just too verbose sometimes.
In college.
Did you see some startup like raised 75 lakh like Indian rupee, like just rebranding Brave
browser.
Yeah.
Browser, yeah.
Which startup is that?
Really? Oh, I did not know that.
One of the Twitter said it's a scam. I don't know about it, but like because they just rebranded like Brave browser.
Oh,
what the name? Starting with P something.
Okay, I don't know about it. Like someone on the Twitter said it. It's rebranding.
There was this another one where there was some AI model or something that was again a ChatGPT wrapper. Again, I saw that on Reddit. It keeps coming.
It's just a AI hype. I think yeah, but this is a interesting question. I actually want to figure out what the syscall is used for. The write-ahead log. I was going through how RocksDB implements it. It's just very extensive to understand. But yeah, I'm not sure. I think DiceDB is a good one for me to go over because I don't know C, I don't know Go.
Okay, I think better way to do that would be like you can like install a like Linux like on the QEMU, and you can like trigger a like write on the RocksDB or something, and like whatever like you can actually debug like with KGDB, like that will you can debug like whatever is happening within the kernel itself. So you can actually see like for that particular moment how which system calls are like getting triggered. So from there you can get an estimate.
Using GDB. Okay.
KGDB. It is like okay. For kernel it's a special one.
Yeah.
Like I need to figure this thing out for one of my like security research. So if you are down to do this, like how to use KGDB, like I think like I didn't know what use it for a long time. So both of us together and like try to figure out how to make this work KGDB.
Yeah, I'll learn from you because I have not. I've used GDB for my Zig programs, but I haven't used it in like a already shipped program like RocksDB. But yeah, I think we can do that.
I was saying KGDB, like we're going to like debug the kernel itself, not the.
Oh, KGDB for the kernel debugging. Oh, okay. Sounds interesting. Yeah. Okay, yeah, we can go through that. I think we can skip a few things from here because you guys already know quite a lot. Give me a second. I think 1 second. Where is that? Yeah. So buffer management is just basically just how databases use memory to reduce disk I/O. I think it just talks about that. There's a few concept called as I think dirty pages, but we know that it's just a page that we've written to, but it's not yet flushed to disk. I think the rest of it is just about what a cache is and the general high level architecture. So it's basically the highest level of the database, all the commands or the language. Then we have in memory, and then we have the backing disk. So that's the general gist.
Acha, wait, like, does it talk about, so this book, it's doing like B-tree based database, right? Like, how does it keep track of these like dirty pages and stuff, and how it,
That part, at least I did not see it in this entire chapter. How it tracks.
maybe others, you can take us through that, like your implementation later.
Yeah, that'd be great.
Sorry, could you repeat that?
I told others, you can take us through your implementation. You implemented this B-tree thing, right? So I'm just interested to know like how this like pages are managed and mapped and flushed. Like how.
Yeah, sure. So, like, very in a very broad manner, every node in the B tree maps to a page in the file. So, if your page is 4 KB, that means each node in the B tree can be maximum 4 KB. Let's say we're trying to insert a node we're trying to insert an item in the node, and it is not possible to fit in the 4 KB. Then you will perform the split. You'll split the node. We know how B tree works, right? So, if the number of items in the node are too big, usually when we draw it, if the number of items are too big, then we split, right? But in this case, since every page is a fixed size, let's say currently our page is for 350 KB, 350 KB of the page is used, then we will, let's say adding a new item makes it 410. So in that case, you will split.
Asha, also another thing, last day I spoke about this B tree, right? So B tree is based on ranges. Like how I demonstrated B tree was like A to Z, and then like in an alphabetical order, and everything is sorted. So when we are inserting these like key value pairs, in that case, how are they sorted, and like how do you decide where it will be inserted?
You can use within a node all the key value pairs will be sorted by key. So I mean you can use binary search, right, and you can figure out what's the correct position, right?
But the key will be in byte representation. So like how?
Yeah, you have to. Yeah, you would have to like convert it from bytes to whatever, or if you can compare it bit by bit, I think. Maybe.
So we convert it to like a binary string, and then we convert like we compare the bits. That's how it.
Yeah, I mean if you know what the data type is, you can convert it to the data type and then compare. Or I think I've seen implementations where they just compare from most significant to least significant, and they just keep comparing bit by bit. And
I think comparing the binary strings, that's makes more sense. Okay.
So both of these structures, this binary tree node representation and the page, both of them are in memory, right?
Just one thing.
Yeah.
It's not a binary tree, by the way. Okay, because like we can have multiple children nodes, more than two.
Just search up B tree. I think it's easier to explain.
No, I explained it last week. You can just check the video, like the video recording.
Right. Yeah, so each node is not just going. So in a binary search tree, there's only one item. In a B tree, there'll be multiple items, and they're all sorted by key. And then if node has like about k items, there will be k plus one child nodes.
Okay.
Yeah.
Yeah. This chapter, I think, just mostly it just focuses on. It's actually very high level. If you say it just ends in like 20, 30, I guess 50 pages or something. But yeah, for the implementation, I think I was mostly just interested in how rocks dividers does model the right hand lock. So I think we'll come to that. We'll cover a few things. Sorry, before that, which is mainly just the overall what a val is, and I think then the concurrency control, and I think then we'll just I look at what I've found on how RocksDB models all these things. I did not get a chance to go over like the implementation details. I did try Tiger Beetle, but they just do a very convoluted thing where they have like two right-hand locks, and the whole language changes because they only speak credit and debit. So it's sort of yeah. Did I? I don't think I went over this. Yeah, I think we already know this, but yeah. Overall, what the textbook talks about is just how a page cache and val are parallel to each other. So we a transaction that does anything that has to do with updates, it first logs it in the val. There's another thing to val. I think it's also implementation specific, but there is another in-memory structure in front of val, which is what the textbook refers to as the log buffer. So they use a checkpointing system where since sorry, not the checkpointing system. For the log buffer and the wall, what the textbook talks about is that the log buffers that represent the wall don't take an entire disk block. So what they do is, if you have an arbitrary amount of size described for a log buffer, they just let it fill up and then force flush everything in a force operation, which is I think again fsync to the disk resident write ahead log, which is just log records for if we just want to check how
This is again for optimization sake, right?
Yep, again for optimization sake.
So it's like a trade-off between being highly durable versus being more being more optimized. Because if the buffer is bigger, then you have chance of losing a lot more, right? Let's say it's in the buffer, but then it crashes before it's written. So if you buffer more, you have lesser chance. I mean, you have more chance of being less consistent. Right?
Hello.
Yes, that is the case. I can hear you. Yeah, we can hear you all.
Oh, okay. I think I lost. Sorry, I think I lost you, others when you were saying something about a trade-off between being highly durable and highly performant. Is that what you said?
Yeah. Because let's say the buffer is a little bit larger. Let's say you increase the size of the buffer, then it's possible that more amount of data is being buffered. So let's say if the database crashes, then you're losing more of the write to the wall, right? As compared to if the buffer size is small, then the wall is updated much more aggressively. So that means you're more consistent. Yeah. But if the buffer is small, then you're writing more frequently, which is less optimized, right?
Yeah.
I guess when we spin up RocksDB or any like key value database like this, do they I think they provide some kind of option where we can control the buffer size for the wall.
Yes. In implementations where they specify whether you want to buffer it or not, and if you do want to buffer it, how much, like what percentage of the buffer has to be full for it to write to disk.
I think that true for wall directory too. Like what I remember is that for Redis you can like optimize like how often the wall directory will be written. Like fsync will trigger how much second like how much time later.
Okay.
Let's get back to the presentation.
Okay. Yes, I think, yeah. So that's about the wall. And the overall architecture is, yeah. So in the first step, you have to log it into the wall. As far as I understood from the textbook, what it says is if in between that the write was sent to wall, if anything happens, then we basically just lose the data because there is no wall in front of a vault. So it's just the primary source of recovery during a crash state of a database. So I think, yeah, that's one thing. So that's why I think this, as far as I understood, all of this is sequential in the sense you cannot modify any page in the page cache that's on the RAM before you log it on the val successfully. So only after that a transaction can proceed to modify anything in the cache page, and then eventually based on the write policies, it's then flushed onto the disk, which is the primary storage. I think,
Are you covering how wall is used for transaction management also?
I think yes. This textbook. Let me just quickly check what else it's covering.
Otherwise, there are a bunch of things like I feel like
Yeah,
add on.
yeah, yeah. I think that'd be great. Yeah, if you can share your insights as well.
Okay.
Should we first go over that? I also do want to interested in that. So should we go over the val and how it works in the context of this? Do you want to cover that? Yeah.
Yeah. I think. I mean, I know a little bit of information. I think I can shed some light.
Yeah.
Okay, yeah. So along with so let's take in terms of let's say key value pair database. So maximum what a wall will have is like a put or a delete. Operations will be stored in the wall, right? So we will also have another operation like transaction start and transaction end. So let's say that in between like a transaction happening, it fails. So what we do is once a transaction fails, we go to the wall and we replay the whatever operations. Let's say there are three operations in the transaction. So it is if T1 starts, so you will record in the wall T1 starts, and you'll perform the three operations, and then you'll do T1 end. So you log that also. So let's say that before let's say after the second operation the transaction failed because of whatever issue, and you'll go back to the wall and you'll replay. So you performed two operations. Let's say you perform two put operations. You will reverse those two put operations, and you'll keep reversing those operations until you reach the starting of the transaction.
Also, when we start a transaction in the wall, do we like have some kind of marker that this is beginning of a transaction? So
yes. That's what I was saying. So similar to how you will log a put operation or a delete operation, you will also log a transaction starts and a transaction ends operation.
Okay.
So let's say, like I was saying, you will do three operations. Let's say two put operations and one delete operation. Those are the three operations as part of the transaction. So you do T1 start, and you perform you will log the three operations, and then you'll do T1 end.
Okay.
Put T1 end at the back, at the bottom.
Okay.
Yeah, so those three, T1 beginning, then T1 end. It's like that, right? So what happens is, let's say in between something goes wrong. So what we'll do is, can you write, like, let's say put three operations in between the T1 end and the T1 beginning. So it's like easier to talk about it.
Yeah, just do like A, B, and C, or P1, P2, P3.
Yeah.
Okay.
Yeah, so let's say it after performing P2, the operation P2, the transaction fails for some reason. So what we can do is we can go back to the wall and we can replay the operations from P2 to P1 and we keep doing it until we reach T1 beginning. So we reverse it. Like let's say if you did put for X key X, we put value Y. So we will reverse that. So what we do in the wall is for each key value pair. Let's say we do put, we will do key value, new value. So let's say,
but in reverse order. So when you're replaying, you go from here to here. When you're adding, you go from here to here.
Yes. So let's say for P1, let's say it's a put operation. You put right key, key X, value A1, old value A1, new value A2.
Okay.
Okay, yeah, this old and that is new. So when you're replaying it, what you would do is you would reinsert X is equal to A1 because it was the old value. So you're basically reversing your operation.
Okay.
It does that. So like even for delete, it will be like that. So when you're deleting, you will keep track of the old value of the key that you have deleted or something like that.
Also, if the transaction fails and when we are replaying, so one thing is like what's the data structure we are using for the wall, and when we are finished
it's just
with
the append only log.
Yeah, I think something like this, right? It looks just rows of just this.
Okay.
That's an append only log because we are only
it's immutable.
We are only caring about the last part. We don't care much about. We don't have a random access. Usually for writes, there is no random access. We don't randomly write at some part of the file. It's always appending to the end of the file. So it's just a log. You keep appending records.
Okay. And if the transaction fails, as we are replaying, once we are done replaying, we also remove those failed operations, right?
Yeah, because we, it's not part of it, right? No longer part of it.
Okay.
Right. Another thing related to this is also, let's say we started. Have I gone? I think it's fine. Even when a database fails, not just about a transaction failing. If the entire database fails, then let's say a transaction started and we performed 2 or 3 operations, and the database itself fails. Also, we would perform the same procedure. Basically, we're moving the database back to its last consistent state. We do the same procedure. We check for which is the last ending transaction, and before that everything is replayed. Like if a transaction hasn't ended, then all the operations that are part of that transaction are reversed, even if a database fails, to move it to its last consistent state. A few more things related to walls is if you're going to cover checkpoints, and also I think there's something called log rotation.
Okay. What? Sorry?
Yeah. Are you covering a log rotation, and there is also a checkpointing?
Yeah, I think any of what I'll cover is just from a perspective of the textbook. It does not go into implementation details. But yeah, correct me if I'm wrong, but what checkpointing, what they talk about checkpointing is, as I understand it, let me just remove this.
So this whole procedure, like there's a name for this architecture pattern is called event sourcing. So it's a really cool thing.
Yep.
Wait, Adarsh, can you speak a little bit about this checkpointing and wall rotation? I guess because when a transaction is occurring, we don't want to flush the wall buffer onto the disk in the middle.
If curly coder hasn't I think if he knows anything, he can go ahead. This is his part. If not, I will.
No, it's fine. I'll cover what I've understood. You can extend on that since you know a bit more. But I think if we just take the example of this, we just have P1, P2, and P3 right here in the wall. And assuming that this is a happy flow, we'll just say P1, P2, P3 is committed to the val. And what I understand is a checkpoint is a way to understand, since val is a fixed size. I think it just takes a fixed size. If we take just 4 KB and assume that this also takes 4 KB for the sake of the example, it will start since this is a circular buffer. It will start overwriting values from the start. But the decision to overwrite new operations into the val is dependent on the checkpoint, in the sense that if P1 and P3, if it's not even this, I think it's just a marker which says that till P3, since we are at append only log, if the checkpoint says that this is checkpointed, it means that all the transactions before or all the operations before have been synced to the primary storage. Is that what it is?
That's exactly right. So any operations that whose results have been permanently recorded in the primary, like the database file, after that it is checkpointed. So the whole idea of the checkpoint is, let's say some changes that you have made are in memory. So we want to know how far up the wall we have to go to replay our changes, because it doesn't make sense to replay the entire wall, because up till some point the file is synced, right? Not everything. Some changes that we make are in memory, and some changes have been written to the some older changes will be written to the file. Newer changes will be in memory, which have been lost. So the checkpoint states that everything below this, it was in memory but not written to the file. So only replay this part. Whatever is after the checkpoint, only that much if you replay, it will be enough to bring the file back to its consistent state. That is the whole point of a checkpoint.
Yeah.
Also, with respect to log rotation, also, so what sometimes they can maintain multiple log files. So let's say an entire file, so let's say a file is fixed size. We don't want the file, a wall file, to continuously increase in size. So sometimes they may maintain multiple wall files, maybe 2 or 3. So let's say that the third file is filled and also checkpointed, or let's say the second file is filled and the last record in the file is checkpointed. So we no longer need that entire file, because we are consistent with the file, right? The database file.
Yeah.
All the operations that have been recorded as part of that particular wall are consistent with the file. So we don't need that wall anymore. We can reuse it. So we can delete all of its contents and start overwriting on top of it. That is the whole point of log rotation. So we don't let the size of the log to continuously increase, because that's not very optimal. So we keep a fixed number of wall files, and once a wall file, like all the operations are consistent in a wall file, all the operations are consistent with the database file, we no longer need those operations. We no longer need the contents of that wall file, so we start overwriting. So it's like a rotation, rotating through the wall files.
Okay. Got it.
That's a nice explanation.
Thank you.
Yeah, that makes sense.
If you guys are looking for any implementations, I know someone who implemented a wall. He was one of the main contributors to DiceDB. Actually, I'll add the repo for that. It's written in Code. Jyotinder Singh, he wrote a wall.
Sorry? Oh, this guy on like second.
No, that would be cool. Okay,
did you say something?
No,
is it this guy?
Yeah, that guy. Yeah, I think he has. If you go to his repository, find very recently, and he also has a blog on it. So I think you can go a little bit down, or you can search for it. It's GoWall.
Yeah.
Okay. Go down. Maybe just search. Oh, there it is. GoWall. Yeah. This one. He actually built this first, and then he used it along with his LSN storage engine.
Oh, okay.
So I think here he might talk. I think he talks about checkpointing as well, and also log rotation maybe. So you can check it out. Also, one more thing that's important with respect to walls is they also maintain a checksum, so that you maintain a checksum for each record that you put into the wall. So we don't want the old values of the record to be corrupted in any way. Yes, so we maintain also for each record we maintain a checksum to make sure that any data that we're reading, it is correct.
Yeah, I think even
that's
this
is a very good repo. He also has a blog on it where he explains also his videos, so you can definitely go through it.
Yeah, perfect. Yeah, I personally, I just find it better to go over, especially code that is written in Go rather than text based.
Yeah, same.
Yeah, I find it hard to imagine.
Yes. Okay, I think we've gone through most of the important stuff related to walls. We can move to the next topic.
Yep. We can. Who's the next one? I think it is Archie.
It's me. But wait, like transaction and concurrency control. So we didn't. Did we speak about concurrency control? This MVCC.
No. That's what I was going to ask you guys. That do you guys want me to cover this, or others do you want to move on to like the next topic?
No. We can do this. I did not know that this was there.
Okay.
Yeah, let's because this is the more interesting part, concurrent. But let's just pace up a bit. Okay, I mean it's going a little bit slow. Let's just pace up a little bit.
Yeah. For concurrency control, I think it won't take us too much time because I was planning to cover the basics. Along with that, I did a very minor case study on how RocksDB does it. So.
Did you have any inputs on how it's simpler, like how walls are implemented in other? I think you had something to say about that.
Broadly, that the textbook talks about. It does not go implementation details per se, but it does have some nice technical facts about each one of them. And so I think before I cover this, I need to cover what anomalies or isolation levels are. So I think I'll just have to use the textbook here. Yes. So, okay, I think this is better. So, the last part where, what it covers is basically what happens when multiple transactions occur concurrently. That's the high level idea of it. And there's a concept which each database sort of has to make trade-offs around, which is transaction isolation. It basically describes the degree to which each transaction, like the so I'll just quickly do this. So the degree to which each transaction can see each other's commit. So if we have, let's say, 3 transactions, like so, and since all of them can have A1, A2, A3, and multiple operations within them, an isolation level defines the degree to which all of the transactions that are making changes, possibly concurrently to just one space in the disk, the degree to which each transaction can view this data or not view this data. That's basically what an isolation level decides, right? And each isolation levels comes with its own set of trade-offs. So basically what they say is how much do all of these transactions are allowed to view one particular key at the same time. Are they allowed to see that after a specific transaction commits or before a transaction commits? That's what an isolation level defines. And there's a side effect of all of this, which is what they refer to as the read and write anomalies. I'll go through these on a high level, I think. Yeah, so we have dirty reads and dirty writes as well. What they basically refer to is, let's say I'll just, let's say if we have something like this, we'll just simply talk about just one storage structure and skip all the val and how it's going to flow through that, but because we want to understand isolation level from its own perspective. So if we have, let's say, transaction 1 that's trying to update something, and we have a transaction 2 that's also trying to update something. So what dirty read says is that a situation where I am trying to read a change from a database that T1 has not yet committed. Maybe T1 has A1, A2, A3 operations in them, but it has done something with A1, but it has not committed yet because it is at the end of A3. So a dirty read is when I read something that might change in the future. Maybe this can fail, or this might just not commit for any reason, right? So that's basically what a dirty read means, is that another transaction is viewing a change that is not yet committed. And same applies for write, is that I'm writing, I think it's, I think it takes similar to dirty read, is where it dirty reads first, modifies it, and then saves it. But in a similar scenario where we might just never reach this stage, and we're just basically doing a sort of a ghost read and a ghost update where we're reading and updating something that never existed after that. I think, most of them. So non-repeatable read is also sort of like a dirty read, but it holds for in a basically tangential scenario where you're reading the same row twice, but you're getting different results. And a phantom read is just an extension of the same concept, but I think, it holds for range queries. I think range, I'm not sure what kind of range queries they mean here. Is it, I'm not too sure about that. That's somewhere I'm a bit dicey in understanding this, but the general idea is
I think it's from like maybe calculating average. Let's say you want to find the average of the values of keys from like x1 to x2, and let's say there's one operation that's performing this average, so it's taking the average of multiple like a range. There's another transaction which is updating certain keys within this range. So it's possible that while calculating the average, you consider the value before it's updated for some keys. For other keys, you consider the value after it was updated by the other transaction.
Got it. So the end result is basically wrong because of some dirty reads.
Yeah, because in some cases you consider the value before it was updated by the other transaction. In other cases, you consider the value after it's updated. I did not understand dirty writes. If you could just explain that again. Dirty reads I understood.
Okay. So, oops. Yeah. So what T1 is doing is
Stuck. I can't hear him.
Yeah, I think there's some network issue from his side. Can you please repeat curly code?
Sorry, was I not audible?
There was some network
issue.
Oh, sorry. Yeah, so let me just quickly start over. So basically what the dirty read means here is that, sorry, you said dirty write, right?
Dirty write, yes.
Okay. We have a value here, let's just say this is 0. And transaction 1 has like 3 operations that it wants to perform. For our use case, let's just say that at each of these operations, it wants to increment x's value by 1. Okay. So what it's going to do and even this also has, let's just say T2 has just one operation called as 1. What it wants to do is also increment x's value by 1. Okay. Both of them want to do the same thing. It's just that T1 has 3 operations within as part of the transaction. So what it's going to do is at first step, it's going to change this and make it 1. And depending on the isolation level, and if we're considering an isolation level that allows for a dirty write, that what scenario would happen in that is that if T1 fails after the first one completed, let's assume that it fails at the operation 2, and at the same time before this is happening, if T2 is allowed to read, and if a dirty write is allowed as part of the isolation level, it's going to say x is equal to 1 plus 1. It's going to do 2. But there is a chance that after this has been done, T1 is completely cancelled. So it now has to abort or basically roll back. So then that's basically a dirty write, is that when you takes an uncommitted value, reads it and modifies it. That's basically what they're referring to it.
Got it.
Yeah, and so these are the anomalies that the database talks about, the textbook talks about, and these are allowed in some scenarios, that whether this anomaly is allowed or it's not allowed is defined by an isolation level. So they talk about a few in this. So there's isolation levels have degrees, like weakest to strongest, and the interesting part is that each isolation level, as far as I've understood, comes at certain trade-off in terms of performance. So the weakest level of isolation that they have is called as read uncommitted, right, which allows for all the read anomalies or write anomalies as well. Read uncommitted allows for any read anomalies, but it's at a very minimal performance trade-off. And the highest level of isolation is serializable. And so I'll also talk about serializable because it's sort of it's a concept derived in other policies as well. So what it does is, let me just remove this 3, and even this has 1. Let's say 1, 2, 3, 4. What serializability does is the isolation level. This has to be implemented within the transaction manager. What it has to do is that for any amount of concurrently executing transactions, T1 to Tn, it has to establish, I don't know if you guys are aware of what a total order is, but it's something similar to that, in the sense that the transaction manager has to figure out for any concurrent amount of concurrently executing transactions whether they can be serialized in terms of the order. This order is implementation specific. The textbook talks about it in arbitrary manner, that the transaction manager has to say that, if I support isolation level serializability, it's my responsibility to now serialize the execution order of T1, T2 till Tn, in the sense that they are deadlock free and basically are chained in terms of their dependence, if there exists any. So if the T1, if any operation within T1 depends on T2, the transaction manager serializes them in terms of that dependence, in the sense that there's no the one that's waiting on something is executed way before, right? So T1 will execute if T1 depends on T2. Sorry, if T2 if there is any dependence, basically it will establish the order in the same way. So it will execute a chain of transactions, but there is a certain trade-off that comes at it, is that at runtime the transaction manager has to figure out if there are any dependency chains within any of these transactions, and then it has to serialize this. Also, I don't remember, but I think it also comes at a cost of lock contention if it's a lock free, if it's dependent on establishing locks for the writes that any transaction is doing. So I think that's one point. I am not sure where it covers that, but
Asha, I have a couple of questions here. So, okay, one thing is it that, like, suppose T1, T2 and T3, we have 3 transactions, they came in at the same time, and then is it the query is it the query planner level that plans how it will execute the transactions and identifies that, okay, T2 depends on T1, so we need to have a proper order that T1 should be executed first, then T2, and then T3, like that. So
I don't think it's at the query planner level. I think it's when the keys come into play, the key value store, or the keys that any transaction wants to modify comes into play. And I think what the textbook says is, it does not go into details, but as far as I've checked, what that basically means is that if any transaction is modifying the same key, and if that depends on some other key, in this case, I think this might refer to the foreign key invariant, because the textbook does talk that the serializability has two important jobs. It has to resolve the conflicts, and it also has to preserve the invariants. So I think it refers to that, where you have to preserve the foreign key constraints, and you have the transaction manager then has to figure out if one transaction is updating something that another transaction depends on. If that is the case, it has to establish that serial order, that T1 completes first, then T2 is completed, because T2 depends on T1 to be completed first because of some foreign key constraint or any other invariant that the database has to preserve. So it is at runtime, as far as I'm understanding from this, and not at the query planner level. Adesh, if you know something about this, or from an implementation sort of perspective.
Yeah, so what I'll do is actually I'm in fifth semester and we had database management systems this time. So we actually had an entire chapter on transaction handling. I have to go through it again, but what I'll do is I'll attach the textbook, I'll attach the PDF itself, and I'll tell you exactly which chapter. So there is a official definition about what it means to like if there are multiple transactions, then there is a definition for what is serializable order of execution of the each operation in the transaction. There's a definition for that, and then there are different types of serializability. There is something called conflict serializability, and there are like other kinds of serializability. So I will attach the PDF and I will tell the exact chapter or even the page. And I think if you go through that chapter, it's explained well.
Okay.
Or what I can do is I can definitely go through it, and maybe in the next meeting I can explain.
Yep.
Okay.
Also, another thing is like in the textbook, has the author mentioned like how we attain locks on like at the row level or table level or database level?
Yeah. I think he generally mentions that there is. He has talked about a simple read-write lock. So he says that there for each item. So they have very loosely defined what a database item is, and then they say that for each item in the database, you will maintain a read-write lock, and you'll maintain sort of a table in which you will define what is the current status of the lock, as well as which transaction is currently holding the lock. It doesn't go too deep into it, but there is definitely a mention. I will attach the file. Just give me 2 minutes.
Okay.
Okay. Okay. Should I move to the 3 types of concurrency control, or you're linking the textbook?
Yeah, I've linked it. I've linked the textbook. You can open it. I will tell you the exact page.
Is this a link or
No, it's it's a file. You can download it. Uh, okay, so you want to go to page 759 in that textbook, and I think so the heading is characterizing schedules based on serializability. So a schedule is a set of transactions. So if I have n transactions which I want to schedule in a safe way, then all of those transactions together are called a schedule. So the topic name is characterizing schedules based on serializability. I think it is very relevant to this topic.
sorry? Did you mention the page number?
759. Uh,
Wait,
it's
this
in
is
the
not
textbook, it's
7:15.
7:15. Yeah,
Okay,
it's
okay. Oops.
yeah,
Okay.
there
I think
you
it's this one.
yeah there. I think from this section onwards, if you go through it, I think it will be very useful. So it'll take a while, but it
Yeah,
is
yeah,
pretty
yeah,
useful.
yeah. Okay. Okay. I think I'll decide.
So they define exactly what it means for a set of transactions to be executed in a serial order. They define exactly what that means, and then there are different ways. So you need to, if there are a set of transactions, you need to determine exactly which operation of which transaction executes when. So for that, again, there are rules. So there is something called conflict serializability. That's what I remember learning. So if you go through that, it will be very useful.
Okay, it's constructing a graph of all the operations, and then it's most probably using graph theory to detect like these conflicts and stuff.
Yeah,
It's pretty interesting.
there is some graph theory involved, but before it got too serious, I think our portions ended there. So
Okay.
didn't go too deep into.
Yes.
It mainly focuses on like how you would schedule the operations of multiple transactions in such a way that it executes in a logically correct manner. That entire section is for that. You go through this.
Okay. Yeah. Thanks for that. So coming
One
to
more
the
thing,
last.
like till when is this meeting going to go after dinner? Yeah, sure. Right.
Yep. No worries.
Yeah, but till when is it?
I will share the recording, so like you can call.
I think other side, this is just the first part, and I think we have some, yeah, like three
Oh,
ones
you
after
guys make
this.
sure you finish all the parts every time, or is it fixed amount of time, like 1 hour, 1 hour?
I think no, because in the chapter 5 was to be covered in like the last Saturday, but uh, yeah, it didn't because the session was the B tree chapter and the one after that, I think chapter it took a while to get through. So
Okay, you guys continue. I will join in like 5 minutes.
yeah, sure.
Okay.
Yes. So for the last part, the textbook covers like the three types of concurrency models that the transaction manager works under. So the concurrency control model does have a say in what kind of isolation levels are supported that go well with the concurrency control model that you're choosing, and subsequently as a direct side effect it also defines the amount of and the kind of write and read and write anomalies that are allowed for a certain database system. So broadly, the first one is optimistic concurrency control, where it assumes that where it assumes by nature that concurrently executing transactions are going to happen less. What that means, what that also implies is that it's going to assume that transaction conflicts also occur very rarely, and instead of using any locks or blocking transaction execution, it just validates and serializes uh, uh, basically before. Okay, I think with that, what it does is when it assumes that the concurrency part, concurrently executing transactions are going to happen less frequently, it doesn't assume that they're never going to occur. It's just that this model assumes that we want to trade locking lock the contention that comes with locking the transactions against having better performance. So it trades in performance for the contention that comes in with locking transactions. So that's where that's how optimistic concurrency control basically what it basically that's the definition of it. And for the case study that I've done here for RocksDB, it does have both optimistic and pessimistic concurrency control model that it follows. I'll come to that once. I'll just cover quickly about what a pessimistic one is.
So in RocksDB, during startup, can do we need to choose which one we want to use, like optimistic or?
Yes.
Okay.
At least for yeah, you did ask about RocksDB, right? Yeah. So you have an option of using either one. You can use a transaction DB, which assumes it's pessimistic, or you can use an optimistic one. That does also define the isolation level as a direct effect. So yeah.
Okay.
Don't know. Yeah, pessimistic one is where it assumes that a lot of transaction conflicts are going to happen. So it's designed for a scenario where a lot of concurrently executing transactions are going to happen, and it does have. I'm not sure if it does have a lockless mechanism, lockless algorithms as well. I'm not sure if pessimistic concurrency control do have any lockless mechanisms. I do have seen the one where they have to establish locks in order to enforce at least some level of serializability in concurrently executing transactions. The one thing that I couldn't figure out is it does seem that serializability is a concept that any concurrency control does have. Pessimistic and optimistic, both of them have this, but it does seem that there's some degree to which serializability occurs. I'm not sure how RocksDB implements it, but I think that's one thing that I want to figure out subsequently in the next few sessions, is that what comes with concurrency, either model of concurrency control, is a very specific kind of trade-off, is what I've understood. In the sense that if we come to how RocksDB provides the trade-off with each kind of concurrency model that the user is choosing, we have two types of isolation levels, right? So one is write committed, the other one is write prepared. So both of them are modeled under pessimistic concurrency control that that RocksDB provides, and then there is optimistic transaction DB, which just works a bit differently. I'll just cover these two isolation levels first. So coming back to the original point, actually, what I wanted to understand, which I'm not also sure of, is that how serializability is achieved within both of these models. The one thing that is not clear is if it's 100% serializable, that would mean that they have to the database has to establish a very complicated dependency chain amongst all the concurrently executing transactions, which is by nature very it has to trade in some level of performance to do that, right? Because any sort of IO operation will have a prerequisite for it to be serialized first, for all these transactions to be serialized first, and we don't know how many concurrent transactions we might get. So that's one thing I'm not sure how it works right now. But yeah, coming to the two policies that RocksDB supports under pessimistic concurrency control, which these two are not covered in the textbook, but I just found it in their documentation, is what they say is write committed is basically a policy that where it allows the data is wherein basically what it does is the data is written through the mem table. This is the in-memory store. Okay. If we are not aware, I'll just quickly check. I'll just quickly go over what a mem table, and this is they have a bit of different terminologies. Yeah. So they have a mem table, what they refer to as the in-memory structure that stores all the key restores. They have an optional log file, if I'm not wrong. They have it somewhere written here. Is that they have they have optionally write ahead log, which I'm pretty unsure why they have mentioned optionally here. We'll have to check the implementation there. And they have a disk residence structure, which they call as the SST table. So generally how the writes flow is through an optionally log operation to a write ahead log, then going through the mem table, and once it's full, it's flushed into the SST file. They do mention that they have levels of SST file. I think that just means if the string keys that are there in the file, whether they're sorted or not sorted, whether they're overlapping or not, that's defined basically by the level at which the SST file is. At level 0, they say that they don't have, they do have overlapping key ranges, and subsequent levels of the
We can't hear. I think
Yes, hello.
I think by some mechanism. I think it's
Wait, can you repeat?
It is
Because
the last few part.
yeah.
where did you lose me? Did you lose me at the overall structure?
you're talking about level 0.
Okay. Yeah. So they have SST files are leveled under arbitrary amount of levels. Where at level 0, it's ensured that it's not ensured that there will be keys that won't overlap. They do have some overlapping keys, but as in the subsequent levels, they ensure that the keys are ordered in some sequence. I think basically that's the gist of it. Yeah, so coming back to this. Yeah, so coming back to this, they have, as I was saying, there's two write policies that they support under pessimistic control. Both of them are, I think, based on logs, but they differ on how the usage of logs is defined basically. So in write committed, if I remember, the data is written to the mem table only after the transaction commits. That's again to the memory. Yeah. So what they basically say is that reads are simplified because you know that that the data you're reading from the memory is already committed, because we only allow committed transactions to be in the mem table in the first place. But there is a significant memory bottleneck that comes with it for obvious reasons. And there's one other point that they say is that the write policy, this write committed policy, by nature cannot provide weaker isolation levels. That's also why it has performance bottlenecks, is because it has to do a few checks before. It has to buffer a lot of things before the actual transaction data is actually put into the mem table. So that's why it cannot support weaker isolation levels such as read uncommitted and all that. So they do also say that there's another option for this, an alternative, which is the write prepared policy, also under the pessimistic control concurrency model, where I'll link this. They have just for this write policy, I think they have a very nuanced technical writing here. I'll link this in the
Acha,
channel.
one thing is this write committed that you told, that when we are reading, then the reading is very easy, because whatever we are reading, we know that it's like already committed. And but when we are writing, then like before committing, where are we writing?
We're writing to a buffer.
Okay.
I checked a few places. They write to a buffer before the mem table. Mem table is like the primary memory storage structure where only the committed data goes. If your commit policy is write committed, there is a buffer that comes before that where they store a transaction's data, and then once it commits, then it writes to the mem table. I have not found the name for the exact structure even in this document that comes before the mem table. I've just seen that it's some sort of a memory buffer that buffers the transactions data there, and I think that's all.
Hello? I cannot hear you.
Again.
Uh, Archie, can you
Amount
hear
of
me?
data if there are lots of. Yeah. Hello.
Okay, I missed for a bit. Maybe my internet was like left room. Okay,
Okay.
go on.
Yeah.
No, it is the
Yeah.
same for me also.
Yeah, I was just covering the question that I think I actually put forth was where does it write before writing before the transaction commits, because only the data that a transaction commits is written to the mem table. As far as I've read, as I was saying, as far as I've read that it's some sort of a memory buffer. I have not found the exact name for that storage structure, but once the transaction commits, then it's put into the mem table, because if the policy is write committed. And also why they were mentioning that this causes a huge bottleneck for at memory, because they have to, if there's a huge amount of large transactions, they'll have to buffer in a lot of data for these before these transactions can even commit. Yes, so there's another alternative write policy for this, which is the write prepared one. They have a whole technical writing on just this one write policy. But as far as I've understood, it's also PCC, but they optimize their logs and divide the write in three stages, where uh, basically you now have the flexibility to commit at two stages, which is at the write stage, where they have the, I think the commands, the actual commands called as put or something like that. And let me just quickly yeah, commands like put that they have. And then you also have the option to commit a transaction if you're in the prepare stage. So because you have these flexibilities that you can commit at either of these stages, that reduces the amount of bottleneck you have for the amount of data that you need to have stored in the memory buffer before you can add it to the mem table. I think the rest of it is pretty straightforward for the flow between after the mem table and towards the primary storage. So I think yeah, I think that's pretty much it from the high level reading that I've done for Rocks TV. Yeah.
So we are done with the chapter?
Yes. Just let me just quickly check.
Did you talk about optimistic?
Yeah. No, I did not. Yeah.
But
Yeah, so
Yes,
I think we just
MVCC
talked
also.
about like two write policies within PCC, but yeah, optimistic. I did not, apart from Rocks TB, I think what they mentioned here is mostly just PCC. But yeah, so what they talk about is that when you have these two options, you need to know about the kind of workload that you're going to get. Because with optimistic optimistic model, what this suggests is that if you have a workload that will benefit from a high write workload, it's better to use. If you think that there's not a lot of conflicts that are going to occur, it's better to use optimistic concurrency control, because it does depend on assuming that you're not going to have high contention or interference between multiple transactions. I think for the implementation part, I don't know how they actually implement this, but the high level understanding that I have is the major difference between optimistic and pessimistic is the assumption for the degree to which your concurrently executing transactions can occur. So based on that, you can choose the policies that you have, that you want. I think that's pretty much it for this. For MVCC, I did not. I did not go over any implementation specific databases that do this. But just for our understand and to finish this chapter, it works on versioning it. It works on versioning each row or each contended row, as a matter of fact. So if we have, let's say, two transactions that want to alter the state of just one row, to optimize for logs, what MVCC does is that since it's log free, what it does is now, because let's say that T1 is read and T2 is write, what MVCC does for conflicting transactions is it establishes a versioning, right? What it does, how it establishes like that version, if it's like a lexical or a integer or a timestamp number, I'm not sure. I think that's dependent on the implementation. But what it does to optimize the log free, the logs, to get rid of the logs, is that if I have a transaction that's reading from this, I'll have each row versioned in the sense that this row itself can have like, this is version 0, and if there is an ongoing transaction that's also writing to this, I'll have a new version. Maybe I think it's mostly just timestamp. So if I say this is, oh, that's confusing. But if I say that this happened at time 1, so we can say that the latest transaction that's updating the state of this row is time 2. So MVCC, what it does is that to avoid locking any row, it establishes that this row is now an older version, and then the read can safely read from the time 1 version of this, but the T2 will now write to a different copy of the same row, which will basically be overwritten once this transaction commits. So that's general, and that's the whole idea of MVCC, that we want to establish versions on the contended rows in order to not block the operations that don't alter the state of a database row. So it's sort of like a mutable borrow and an immutable borrow. So you can have a lot of immutable. Sorry.
So it writes to a different version of the same row, you're saying, and then after the read is done reading its version, that old version is updated.
Yes. Yeah.
Okay.
And then sorry.
So this is to prevent locking, but the whole idea is that you're maintaining, if multiple transactions are trying to write, then you'll have to maintain one version for each write, right?
Yes, and I think what it does is, let me just quickly check. If it talks about the add wins or the update or the last add wins, it doesn't. It's just very brief. But as far as I know, there's also ways to do that, in the sense the last transaction that's writing will overwrite the subsequent ones, and but that will also depend on the write policy that you have. If you have a stricter write policy, which means that if you are serializing your writes, that would mean that each write will actually have to maintain its own version, as you said, and then override the previous subsequent write transactions. It does have that override, yeah.
So, okay, if I understood correctly, you're saying there is some versions in which all the write transactions are writing to, like they're writing on top of each other. Is that what you said? They're maintaining only one updated version, but they're all writing the same version, all the write transactions. Is that what you said?
Yeah. But I have yet to find that the implementation specific part of it. But as far as I know, that depends on the write policy that you have configured. For example, for if we are saying that we want the highest level of isolation level, that would mean that we don't allow any sort of write anomalies, right? And that would mean you don't allow any concurrent transactions to happen. So if there's if there's multiple write transactions occurring concurrently, if you have a write policy that dictates you want serializability, only then will the scenario happen that all the write transactions are establishing their own versions, updating the record.
Okay, so otherwise all the write transactions are updating one new version, and the last transaction to write will dictate what is the updated value of the next version.
Yeah.
Okay.
Yeah, I think that's pretty much it from me, guys. I think it's better if we go through like an actual implementation of all these things, because if you guys agree, obviously, but yeah, I think like this textbook goes into introducing us to the internals, but the implementation involves like a lot of scenarios that you need to think through when implementing these. So, like for example, I think
the book is more about like for an engineer to understand how he would use this kind of object without actually implement. They don't worry about how to implement something. They worry about like an engineer should know what this is so that he can use it to build a bigger product.
That does make sense, because with this, at least with this concurrency model, I don't know if I'm able to use RocksDB. Depending on the workload I have, what kind of write policy to use. Yeah, that makes sense. That's why I think this book is sort of high level. But yeah.
So just to clarify, you use optimistic concurrency when there is not a lot of contention. Because let's say if there is a lot of contention, then it's so let's say something is reading, it read a value and it read its version. Let's say the next time it reads, if the version is updated, then it has to redo all, like it has to reset, right? It has to perform all its operations again. So the only way that something succeeds if it reads the version and the next time it reads, if the version is the same, then only then it can go forward. Is that what that is optimistic, right?
Yeah, exactly.
So if there is a lot of contention, then it's possible that transaction constantly is being reset again and again. It fails multiple times. So we don't want that. So only in cases where there's not much contention, you want to use optimistic.
Yes, exactly.
Okay.
I think with that, we've come to the end of the chapter. There's a few things I did not go over, like the steal and force policies and all that stuff. But yeah, I think.
Yeah, also one more thing, what app are you using? That the previous one, black background app. I just like the interface.
This one?
Yeah.
This is Obsidian, but I do have a few plugins added to that.
Okay, it's free, I'm assuming.
Yeah, it's free.
Okay.
Sorry?
What are the plugins you're using?
Oh, there's a few.
Just put that in the chat and we can use it.
Yeah. I'll just put up my setup in the chat later. Yeah.
Okay.
Okay, guys.
For like file format, like the B tree is that like for every nodes, like they're like set for a for a page, like the page size vary from 4 kilobyte to 16 kilobyte, and like these are access to like, okay, these are the thing we already know. This is mine. Okay, so like there's like few things like we need to like there's few requirement for like optimal B tree within the disk. So that will be optimized. That file format will be optimized for like storing like B trees. So they just like talked about that on that thing, but there's like few things that say there like for example in the RAM, it's the data layout is pretty easy, like because there's no concept for like offset, and the like there's like many things that is handled pretty easily on the RAM, like on the like memory, but on the disk we have to think about like other stuff, like how large chunk of memory are like handle large chunk of memory, and like other different things that is according to the book, like that is easy on the memory. So, for example, variable length feels from what I know, like on the memory, that is the difficult too. Like for example, take advantage of CPU cache line, like that's a difficult thing too. But they're talking about like oversized data handling on memory is more straightforward. I don't know how that is more straightforward. Because like for Zig or like other languages, that is pretty difficult. I don't know like in what sense they're talking about this. Okay.
Is it like having a very large key value pair? That's what it.
Something like that, handling variable length fields or oversized data.
Okay.
So they're talking about like pointers, but still like I can see that for a really huge chunk of memory, that maybe that is sometimes the case. But if you have like primitive, the primitive like integer type, that size can vary a lot. Then you need to do something about it, right? Like you cannot just it's not just pointer. So I don't know. Like I need to look into how other people do it. Okay.
Okay.
And they're saying again, there's another example that like on the for the disk we don't have primitive like malloc or free, like we can only read and write. So that's why they're saying it's like much harder. So this part I can somewhat see, because like for malloc we need to just mention the size. We don't need to do like think about other part. But from the file format chapter we can see that like for writing on disk we need to take other considerations. So like everything is like binary encoded on the disk, like everything is written in binary. So we need to think of that whenever, because like we need to deserialize, and we need to for the communication protocol, like we need to think about the binary format. Okay, so there are primitive types, like we already know about this integer, date, string, stuff like that. But there's another thing we need to think about, that is the Indians.
Indian
I'm not
method.
sure how to. Yeah, so you know about this already, right? So the like big Indian, or little Indian. Big is the like the most significant byte start, like in the address, the most significant byte start, like A is the first address, A plus 1 is the next, and so on and so on. So
Okay. So what do we need to
Yeah.
care about it? Like.
okay, and I'm coming to that. So for example, that like this thing like varies from one operating system to another. So like and what is the word? So before doing this kind of thing, I think at the time of initializations, like database initialization, they have to take consider of that, like how what kind of endian it is, like how the data is stored, because like offset and like like offset comes into play here, and like other different things comes into play. For example, like I'll come to little later, like how the enums are stored, like lots of like binary values, like flag values are stored within like 8 bytes. Like for example, it like 8 different flag can be stored within 8 bit or 1 byte. So how they are stored, that ordering is going to be dependent on the Indian names. You understand what I'm trying to say here?
Yeah.
Yeah. Yeah, ask me if you want to ask anything.
No, wait. Can you repeat it once again?
Yeah. Oh no. Yeah. Yeah. So okay. So like for instance that there like okay, let me go to that part. So there's some flag, right? Flag is like when I'm saying flag, that means that some informations about like for about that can be about the page. Like for example, is the page is overflown? Okay, is the like what is the word? Is this a leaf mask?
Okay.
So or like there can be many different things, variable size values. So they are stored as bit inside a byte. Okay.
Okay.
So when they're stored in this way, like you need to like read it from
Okay.
like
I understand. Like
from left
if
to right. They're going to store in certain way, left to right. So whenever you're going to like they're
so like
stored in somewhere. Yeah.
first variant, then it's like the first bit we flip it, we turn it on,
Yeah.
and the remaining will be 0. But okay,
Yeah. The mask.
then so if the enum is very big, then that like corresponding byte size which is representing the enum, that will also be pretty big.
Uh,
So like if there are 50 variants, it will be 50 bits, but like rounded over to like that many corresponding bytes
yeah.
basically.
No, yeah, no, but the concern of like
52.
Indians come here, like whenever you think like you need to mask, like you need to use some sort of mask to get that value out, right? So
Huh,
the way,
I understand,
yeah,
because it depends on the Indianness, that let's say
yes,
we have the second byte, like okay, if there are, suppose there are 50 enum variants, so
yes,
we will have 50 bits, but then okay, like
yes,
we need to talk in bytes as well, so round it up to 52, because 4 8s are 52, so it will be
yes.
8 bytes. 8 bytes.
Anyway, so where does it start from and how the mask, like where the mask value should be, right? So because when you were reading, like you need to sort on the marks in certain way so that you can. Is it from the beginning of the beginning to 8, or is it from the end to the 8? So that's
Yeah.
how it is.
Yeah, like if
Yeah.
we have byte 2, then like is it stored in reverse order? The byte is stored in reverse order, or in normal order, depending on the Indianness. I understand. Okay.
Yes. So, so this is like yeah. There's some few things like that is used like K little Indian. Like I think this is some sort of variable like operating system sets this value so that you can you can understand how this is like how this is. So you can there's some sort of like I think I'm not sure what this is because this is another link, but I'm guessing this is some sort of syscall or something like
Okay.
some famous function that you can use to like reverse the order of the bytes. Okay, so the records are like okay, we already know this. Like we have to serialize this thing, like we all know about this. So bytes are 8 bit, long are 8 bytes. So there's another thing is that single precision float number is like the float or the float in most of the languages, and the double is the double precision. So it's represented with IEEE 754 like arithmetic. So fast okay, this 8 byte represent an exponent and the first 23 byte like represent a fraction. So this is all with the like logarithm table and the exponent table like for floating numbers. Okay.
Like if it
Then
is 6.57, then 6 is the exponent and like 57 is the fraction. Is it so, or what?
okay, which part you're asking me about here?
Yeah, the representation. I forgot. I read about this, but I forgot. Like.
Yeah, okay, so how this is like there's some sort of like table like logarithm kind of table. So there's some sort of precision, so it's not exactly precise. Maybe it would be like for single precisions. I forgot, maybe it's precise till 16, like after the fraction number, maybe till 16 points it's like it's precise. So how this is stored here is that like there's two value. One is I think in terms of, I think it's in terms of logarithmic table. Like one is one is like value of exponential, another is that like what you get after doing like logarithm of the actual fractions.
Okay.
Something like that. It's from some table.
Okay.
So it helps you to like compact the data size, but at the like it's not going to be precise after some certain value. So you just need to be aware of that. Okay. Okay, I think this is 16 bits. Single precision is like precise till 16 bit. 16 value after the point. Okay. Okay. So there's like another there's two concept for like how the string data is stored. One is pretty easy, like you're going to put the size and you're going to have the data for that. Yeah, but there's another kind of way to do this, like is the null terminated string. So whether like it's gonna happen like when the reader read still there's a like end of string symbol, like just like the like C++ handles it, or like many other languages handles it. So this is like much like little bit faster, like because like you can no sorry the previous one is much faster, like you can understand the length like in constant time, like instead of like you don't need to go iterate through it, like that's it. Okay, so there's bitpack data, like what I was talking with you about little later, batch booleans in group of 8. So here like so the example they give is that like for node type like that can be like root is this internal is this leaf. So this kind of like information that is like repeats a lot of time, that's going to be that's going to be like packed in the enum. Okay, there's another information that I like really liked. So like when the data is going to be put in the disk, there's like another caveat to it, like for example whenever like we like start, so it's depending on the architecture type, whenever we're like writing start in the disk, the compiler itself can add some padding to the structure, and that is going to be like architecture dependent. Okay, so there's another caveat that I really liked. Okay, so if I go to next,
can you go back to that?
Ask me. Ask me.
You can combine primitive values into structures, and no, I didn't understand what you say. So in C struct we have
okay, no. So what he's trying to say is that like there's like primitive types, like the primitives as in like integer date string, but there can be much more complex like data representation, right? So for that there can be a struct for that to get a more complex. For example, that think of like real number like complex numbers, right? That's you need to have a struct for that, things like that. But for that we need to think that like there can be some padding added by the operating system, but that is for C. I don't know if that is gonna happen, like it's okay. So I already talked about flags, like it's gonna combine like multiple booleans and enums in like in a single like in a packed way. So it can be fixed size or like information about fixed size or variable size. Okay, so then there's like general principles. Okay, so this part, like this is the thing I don't like, but because they're like GLP, there's like it's actually like written nothing here, because like all the possible things they say, yeah, this can happen and the other thing can happen too. Like for example, they're saying addressing can be like addressing can be file format. Addressing can be like split into the same size spaces. Oh, like there can be like a single block or multiple contiguous block, or like but that not always be the case. It can be like they're saying it can be. So then there is that like most in place update storage are like uses like the same page, like all the page sizes are the same. Okay, so because like makes like read and write like much easier. And there's like append only data storage too, like that works in the same way too, like it's the same page size, and it just append on the end of the memory till it's like till the memory is filled up. After that like the f sync happen, the file sync, I think.
Okay.
I'm not sure like what fsync full form
Okay.
is, but
I
okay.
mean, what is the topic of this general principles thing? Like, okay. So
Okay,
suppose
I read it few days ago. Let me. Okay, this is the like file organization. Like there's like they will go through the multiple thing like variable, a variable length field and like fixed length field.
okay.
So these are the top things he talked about. Okay. So the file is like they always start with fixed size header, like and like fixed size may end with fixed size trailer. Okay, there's another may always may. Okay, rest of the file is split into pages. Like every file is like split into pages. So and like again like let me reiterate that like I think you already know that, but every node is a like sorry each page is a like node or the so in for B tree node and page are used the terminology are used like in like interchange like at this like like same like interchangeably because like both of them represent the same thing on this case. Okay, so
Okay.
we already know this. Like if the schema is like fixed, like when like it's the amount of like data that is going to be stored on the disk that's going to be really compact because we don't need to like save like how much the like variable size field is going to occupy. You
Okay.
understand this part, right? Because if all the fields are
Yeah, I
going to
mean
use the
it's
same amount of data. When I'm saying same amount of data, is that like one type of primitive, they are going to use only one type of like fixed size field. They're not going to be in a variable size field. Then the page is going to be data store is going to be a lot like compact. But if there's like variable size field, what's going to happen is that like they're going to store when the fixed size field ends like after that part.
okay.
So the way it's going to be happen that at the end of the fixed size field they're going to they're going to be value like for example first name. So first name length will be stored at the end of the fixed size field. Same for the last name.
Okay.
Okay. So
And what if this whole entry is, let's say, suppose occupying 5 pages, like 5 page size, it's equivalent to that. Then,
okay. So I didn't understand this part. Can you repeat?
suppose this whole entry, like one entry we are doing, and that whole entry is, the size of that entry is like 5 or 10 pages. Then, what will happen?
Okay, so the one you're talking about, like this is like for most of the time, you can think of like blob, right? So blob is like talked about later. There's like slotted directory and stuff like
Actually,
that.
slotted pages we can skip because
Yeah.
we already.
Yeah, you already covered it, but that is like covered with blob, like for the to efficiently store variable size records such as strings, binary large objects like the slotted page and slotted directory. Yeah, that is already covered somewhat. Yes.
Okay.
Okay, so like fields composed of primitives. Okay, wait, yeah. Uh, okay, so there's like building hierarchy. Like so, there's fields are composed of primitives. Each field is composed of like primitives, and cells composed of fields. Like this is one cell, like for the table, like one of the example. One row, like so. Pages composed of cells then sections composed of pages. I actually forgot about the sections, but I think we have already discussed about it. So these are the thing. Yeah. To have so there's another optimization that can be done is that like there can be stored about the offset like offset can be like stored here so that like we can just use the offset from the where the fixed size field ends to move to the like for example we want to go to the last name. We don't need to calculate like how much the first name is. We can just like if there's like 5 to 7 different variable length fields, we need to calculate like to go to the seventh one we need to calculate what is the size of all 6. So we can just store the offset so that way we can just skip over there, right? But we need to save the size too because we need to know like why it ends. Even though you can do it with offset too, but okay. Okay, so after that there's like page structure. So yeah, I already talked about it that like 4 kilobyte to 16 kilobyte. The database are partitioned into data in index files and on disk B nodes. Okay, so from structure, this what I told you earlier. That from structure perspective, in B trees we distinguish between leaf nodes that hold keys and data records pairs, and non-leaf nodes that hold keys and pointers to other nodes. Okay, you understand this part, right?
Yeah, I talked about this last
Yeah,
time.
you talked about it. Yes, yeah. So each B nodes occupies one page or multiple page linked together. So in the context of B trees, the terms nodes and page are often used interchangeably or even block. Okay. So the fast implementation of B tree paper, like that just had like like continuous, like it didn't, like it couldn't handle the like variable size data. It could only handle like fixed sized, and you need to relocate every time something happened. And like just look like here's like piece the pointer to the child pages. The key, this is the key, this is the value, then there's another pointer key value, so they are contiguous. So every time you need to like free up space or something, like there's everything's there's you need to rewrite stuff. Okay, so the main problem we like, okay, there's like multiple problem, but most difficult problems that can be said is that the like how can you reclaim space? Like for example, the one of the record is like fixed. Okay, for example, make it easier, either the K2 or V2, both of them cleaned up, like they're not necessary or they're deleted, or even the page P1 that okay, no, that's I shouldn't say that, but K2, V2 or like some other value have been like cleaned up. So how can we efficiently like use that space, right? So because if we try to put another value in there, the value needs to be like exactly equal size, or otherwise like there's like we like
There will
space
be
can be
gaps in
wasted.
between.
Yeah, or if we make the like slot, can make the slot like really large, so that like whenever something gets deleted we can put other stuff. Like there can be like waste, like space can be wasted too, right? So like if we make the fixed size segments instead of like like contiguous memory users, so that's another problem. So by thinking about this thing, like we can think that the file format, ideal file format, need to fulfill like three things. It need to store like variable size records with like smallest overhead, and it need to be able to like reclaim space. So and like one of the way reclaiming, like best way to reclaim space is that like we can rewrite the page and moving records around, but even though that is expensive, but we'll come to that like when we need to do it. Okay, so after that, like we need to like, for example, the whenever there's a like non-leaf nodes, so then that need to like they need to point to some record in some other leaf nodes, right? So out of page like reference, that need to be in efficient way. So like without like putting like exact information, because things can vary. So that's the thing. So they talked about slotted page, like you already covered it. So I looked into slotted directory, and to me, like from my understanding, like it's like slotted page is more efficient. Slotted directory has much more problem to it. I can be wrong about it, but there's like a few cases it can be better, because we need to be like it needs to be more predictable, and like but it cannot handle fragmentation. It cannot it can handle like what is the word, but everything needs to be fixed, like fixed length records, like
Wait,
what I
but,
remember for
slotted.
slotted directory. So slotted page is like way more flexible, and its performance little less than slot directory, but it's better in like for practical uses.
Okay.
Use cases. Okay, so
But
we
what
already know
is
about like
slotted
how
directory? I
slotted
don't
page is,
have.
like from like, but there's going to be pointers on the beginning of the page, and it's going to point to the end of the page. Yeah, and there's going to be header on the beginning, like that's going to have some sort of information of the about the page. Yeah.
Okay.
Okay, so let's see how it covers like all three like requirements we talked about earlier. So the first thing is that like is very minimal overhead because the pointer array is holding offset, right? So exact location is there, so space reclaim. So we can do some sort of defragmentation and like rewrite the page. That's one thing. But there's like other things they talked about, like because like we're going to talk about that later. So there's like dynamic layout. Is that like the slot? Is these slots can be referenced by ID to the pointers. So I need to look into this later, like how this actually works. I tried to look into like SQLite, but I didn't understand that much of it. But this can just I'll try to like come up with the next day, like because like I'll go through SQLite more.